Hey, what's going on, everyone? It's HVAC Jake here, and this is my co-host Julian Finbow.
Hello, how's it going?
Good. Yeah, another day. We're gonna talk about all things HVAC here on the Push Pull podcast. So, what are we gonna talk about today?
Right on, man. So we're going to talk about pressure testing today. So pressure testing is a important topic. It kind of gets, I would say, pushed aside because it might be something you get your apprentice to do and not think anything of it, or at least maybe some people and some mechanics. But it's as important as charging and evacuation, and there's some nuances to it, especially when you're talking about small versus large systems. So that's what we're going to cover today, Jake.
Yeah, right on. We're gonna kind of focus on more of the commercial industrial pressure testing. I worked at Johnson Controls, and I worked on a lot of big equipment. So there was a lot of things that I encountered during pressure tests, and going to be using a larger volume of nitrogen to pressure test than if you were working on a smaller unit, just carrying around a little tank of nitrogen. Right, I would bring in multiple tanks, or tanks with headers, and bring lots of nitrogen in to fill these vessels, anyways. And same with Julian.
Yeah, that's right. So you're in the chiller world, I worked in the ammonia world. Using a manifold and that kind of stuff is like normal practice for doing a pressure test, right? And I remember talking on the phone, after our days at work or whatever, and you had some interesting points about chillers and live systems and low pressure chillers and stuff like that. So that would be a cool thing to bring up if we have time also.
Yeah, for sure. Yeah, every chiller has its limitations, and you can only pressure test to a certain point. So if you're working on, let's say, a high pressure chiller on 134A, you can pressure test, I don't know, let's say about 100 psi, somewhere below the reliefs on that system, right? But then if you're working on a system with R123, those pressure reliefs are set to 15 psi. So you really only want to pressure test to about 10 psi unless you're doing a major repair. Then you would take out that relief valve or the rupture disc, which is used on the low pressure chillers, and you would block it off or put a plate there, or try and take that out of the system, so then you could pressurize it maybe to 25 psi. But also, when pressure testing a low pressure chiller, you don't want to introduce a whole lot of pressure to it because it never really sees that. It's only really going to run up to about 5 psi on the high side. So you don't really need to pressure test it that high because the chillers are actually designed to run in a vacuum. So some of the flanges don't even have a gasket in there. They're just they have a flange sealant, which is Loctite 515. So
Okay.
if you pressurize that too high, you end up pushing that gasket out of there. The gasket 515, the liquid gasket, not a physical O-ring or something like that. So just things to be considered of, right? Different industries, right? If you think about a normal pressure test on a small system, you're thinking, 134A, R22, 410A, high pressure tests. But on the chiller world and even industrial world, it's a little bit different. There's other things to be considered. So
Yeah, that's cool. We talked about this in a previous episode, R123, but I had to look that up. I mean, not ideal. I should be sharing my screen, but I don't think this is mirrored, the Ref Tools app by Danfoss, like that's hilarious. That's a saturating condensing temperature of 120 degrees at, 15 psig. So
yeah, yeah, it's a very low pressure refrigerant.
And it's like the thing about pressure testing also is it's what you're trying to prove to yourself on the system that you're working on to verify that it's correct. And then maybe someone in the office doesn't have the same opinion as you, or they don't understand what you're doing how you do. And then there's the customer. So it's kind of like you're ultimately doing it to make sure that the system is tight and it's correct, but sometimes there's a bit of communication or confusion between yourself and another person that's related to the pressure test. So I mean, we talked about stuff like that before too, right? Like what other people are trying to see from the pressure test that you're doing.
Hmm. Yeah, every situation is different too. Like if you're doing installation, you might have to get a governing body in to come and inspect your equipment. So you're going to follow those regulations, right? And if you're doing a big repair on a chiller, you got to know the limitations of that chiller, and there might not be that governing body coming in to inspect it, but they will inspect things like pressure relief valves and other regulations on pressure vessels and stuff like that too. So I never really experienced any of the installation portion of it. I was mostly service based, but Julian did a lot of installation and new buildings and would have TSSA come out and inspect. So what kind of whatever they're looking for, that's the pressure test that they would have to see on that system. So.
Yeah, and I was about to ask you about that before we get off the topic of chillers. I kind of wanted to ask you about the stuff that you did, like what your experience is having to bring TSSA in, because chillers are weird. They're a big capacity piece of equipment, but they're all contained in like one area. It's a refrigeration system. It's really powerful, but it's not like it's spread out over like thousands of square feet of piping, et cetera. So like, how does that work, Jake? What's an experience, or how does it work when you have the TSSA have to come in? How does that work for chillers?
So I never had TSSA come in for me. I never had to request them to come in, but they would do site inspections as I worked at like the hospitals and federal buildings and other plants and stuff like that. They do regulate the systems under the pressure vessel act, I believe it is.
Yeah.
And really what they're coming to do is verify that the relief valves are within the 5 year um, term. So the relief valves need to be under 5 years, or they need to be serviced or replaced. And generally, it's cheaper to just replace them. And they'll also look at the safeties as well. So they're going to look at like your high pressure control, low pressure control, any kind of manual reset controls, and verify their calibration or that they've been calibrated. So that's something we would do kind of on an annual basis, right? We'd check the relief valves, make sure they were still valid, and make sure all the safeties are calibrated. And there's many different methods to check the calibration on all the different controls. And we put a sticker on there, say, okay, calibrated this year and
Yeah.
verified. And that's what they would look for. And they also wanted a logbook as well to kind of keep with the
Yes.
chiller, to just show the service that's been done, and everything's been properly maintained. Really, that's what they're looking for. So I've had quite a few inspectors come by and ask for that information, and I
Hmm.
was able to provide it to them. So.
Yeah, right on. So I definitely relate to you on the logbook and the certifying your safeties every 1 year. So what I used to say about relief valves teaching apprenticeship is that you change a relief valve every 5 years, unless it's too hard to get to, then you just don't change it.
Yeah, that's a good rule of thumb.
Think in one beat up food plant you might have in your head, and there being relief valves up in this touching the ceiling that I found they didn't get changed for 10 years and no one ever knew about it. And then we did. I'll talk about that actually because I want to ask you about the same kind of thing. I guess a little bit of a jaunt from pressure testing, but changing relief valves on a live system. So this is, I guess, one of maybe two experiences I had doing this. So they're on a suction accumulator, again, up in a spot that's hard to get to. And because there's no way to easily isolate it and there's no relief tree, and when I say that, I mean a relief manifold, which is just two fittings for two reliefs, and you can close one, change it, move the tree valve over, and change the other one. Sorry for saying relief tree. It's a moaning thing, maybe. Anyways, not having that, you have one relief and you have to change it. So we didn't want to shut the system down. So we ran the system, but we adjusted the low pressure control so that it basically ran to a slight vacuum, like 5 inches of mercury vacuum was kind of the target. We had it down like lower, but so the mechanic was down at the control, making sure, the compressor was going to stay operating. And I was up on a ladder and pulled the relief out live, pulled a bit of air in and stuck the new relief on. And then, Uncle Bob came through. So earned my paycheck that day. What about you, Jake? What's some scenarios where you change relief valves, and how does that work on like a low pressure chiller, high pressure chiller when it's not practical or easy to isolate them or take them out completely?
So in the trade, we call that on the fly.
Yeah.
So if you can avoid taking all the refrigerant out of a system and do something live, it is, how do I say this? It's not the most correct way to do things, but if you can make sure it's controlled, then it's definitely a lot more efficient. So, to that point, on a chiller, most of the chillers have one of those manifolds where you can isolate one side. So you're going to move the valve over, and there's two relief valves there, so you can change one and the other without even disrupting the service of the chiller. But sometimes they have a straight pipe to a relief. And what you can do is you can pump down a system or move the refrigerant over from the evaporator to the condenser and isolate it and get it down to 1 psi, 2 psi, very low psi rating on a high pressure chiller,
Yeah.
like 134A. And you can spin it out and put the new one on under pressure. Then you don't introduce any air into the system. So
Yeah.
it is definitely something you can do. And if it's done correctly and safely, then you can do that. If it's in a awkward spot or you're not able to do that, obviously you got to remove the refrigerant, pull the valve out, replace it, and then pressure test, as we're going to be talking about shortly, and add the refrigerant back. Right. So um, there's definitely been lots of times where I've swapped out components, at a low psi live. And then if you're working on a low pressure chiller, they have a rupture disc. So that's the type of relief valve that they have. And you can actually pressurize these chillers with hot water. If you run hot water through the water side of the chiller, you can bring that pressure up to zero. And I've swapped out rupture discs that way as well. So you're only, bringing it up to basically 0 psi, or actually on a low pressure chiller, you're bringing it just below 0 psi. So you are probably sucking in a little bit of air, just like Julian was saying on his ammonia system there, because you don't want the refrigerant to escape. So you just don't want to open it up and suck in a whole bunch of air, because then you're going to have to get the air out of the system. But if it's just below zero and you're not releasing the refrigerant out, then you can swap it out that way. So.
Yeah, good. And like I can sympathize with you on relief valves being in ignorant spots, right? So if you have an open area and you feel safe doing the task on the fly, like you say, that's one thing. But sometimes because of safety and it not being worth it, you just you just do it the straight up way, right?
Yeah. All right. So why don't we get into talking about actually pressure testing these systems here? And we'll just kind of do a little bit of introduction on pressure testing the bigger equipment here.
Yeah. To swallow the bug. Yes, Jake. So the designation for small systems to big systems, there's many things, right? There's, like I said, a weird thing like a chiller where it's very high capacity, but it's in a contained area. So is that a big system or small system? So what it is, and you can find this information through ORAC, ORAC. It's an Ontario governing body, as you'll see if you look it up, that for categorizing a system that requires a TSSA inspection, you're going to be above 3 tons for refrigeration system, and you'd be above 5 tons for an air conditioning system. So at that point, if you're going to do a new install or major modifications to the system, you are supposed to have the TSSA come in and do an inspection. So we're working in the Toronto, Canada market. So the TSSA is the Technical Standards and Safety Authority, and they're the body that's going to come in also for natural gas stuff and propane stuff. But for refrigeration systems, they're going to be coming in to check out pressure tests, refrigeration installs, and then like Jake mentioned, if there's any kind of boiler pressure vessel stuff happening, they're also going to be taking care of that in this area.
Yeah, right on. All right, so I just want to kind of run down going through a pressure test on a chiller and kind of some of the things you might encounter on here, versus a smaller system, right? Most smaller systems are hermetic and they got copper piping and some steel components in there like the compressor and stuff like that. But everything is usually welded, and you don't have a whole issue on expansion and contraction and stuff like that. But when you're working on a chiller, you have O-rings, you have flare fittings, you have steel, you have copper, you have brass, you have gaskets. So all these things that could pose a problem when you're doing a pressure test. So when you're working on a big chiller, when it's active and there's refrigerant in it, you can do a pressure test on it while there's refrigerant in there. You can use an electronic leak detector and go
Yeah.
around and look at the whole chiller. And if you detect an issue, then you can move forward with doing a repair that way. So that's one way we can check, the pressure in the chiller, right? So annually, I would do an inspection on these chillers, use an electronic leak detector, and if I noted any leaks, then we make a compile list of all of them and come up with a game plan on how we were going to repair that. And if the chillers were leak free, then we would just proceed with doing our annual maintenance, and then we do another leak check the next year. But if you were doing a big repair on this chiller and you removed all the gas out of this chiller, you would want to pressure test it again to verify that the repairs that you've done are leak free. So, yeah, like I said earlier, you're not going to show up with one little tank to fill up. Let's call this chiller behind me is about a 550-ton chiller. That little bottle, the volume in there isn't going to fill the chiller, right? So you might need, let's say, 4 or 5 bottles, right?
Mhm.
So you're going to come in with a whole bunch of bottles. You're going to pressure test this thing to the appropriate pressure for the equipment, and you can go around and you can leave it under pressure overnight. You can do a 24-hour pressure test and come back the next day and verify if the pressure remains the same, then you're good. Another thing that's a common practice on some of the bigger equipment is putting in what they call a trace gas. And every manufacturer has different recommendations on what you do. But in the past, what we would do is we would use R22 vapor, just a very, very small amount of vapor mixed in with the nitrogen as a pressure test. So we could pressure test the chiller and use our electronic leak detectors to find a leak if there was a leak.
So you're
So
actually allowed to do that, Jake?
it's in the literature.
Because I've done it. I didn't really think about the
Yeah.
perspective.
I've read the manual for some manufacturers, and they do recommend that as a procedure to do. So if you do a pressure test and over 24 hours it holds, then you don't have to do that. But if you're having issues, and because there's quite a few fittings on these bigger equipment, you can do that so you can kind of expedite the process, right? So I wouldn't do that as a first resort. I would just do a pressure test with nitrogen,
For
and
sure.
you know, uh, you leave the pressure test for 24 hours, and then come back the next day and verify the pressure. So
Yeah, good. And if you need to find a leak for your quota, Jake, it's always a Schrader valve, right?
yeah, leaky Schrader valves. That's what you put on your work orders always if you can't find a leak.
I want to trail off what you said about, getting the system to a condition where you can see the leak. So in refrigeration systems, on an evaporator coil, you can have a leak only under certain conditions. So, or you can have a leak that's small and you're in the process of repairing it. So if you think about like an evaporator coil that runs at a slight positive pressure, like say it runs at a 5 psig saturated suction pressure, whatever refrigerant, whatever the temperature is associated with it. You're running at 5 psig when you're in cooling. If you have, a customer complain of a leak and you go in there and you find the leak and you tighten it up and walk away, when you go into a defrost, you could have a condition where there's way more pressure in there, right? You go up to like 125 or 150 psig, and then you have a leak in a different condition. So I just want to note that for a couple of reasons with refrigerant in the system, it can be helpful to operate the system in a way that's going to make the leak be basically as bad as possible to see if it's leaking under that condition. So for evaporator coils that have hot gas defrost, it's always important to check that out, right? If you're repairing a live leak, so you're going up to the unit, it's like a flange, a 2-bolt flange, which is the worst thing ever, and you're tightening that up, which you obviously have to be careful. You can only do so much with a 2-bolt flange. You want to make sure that when it goes into hot gas defrost and you have that big temperature swing, the piping moves around, expands, and you have a lot more pressure, that you're also not leaking, right? So that's kind of an interesting thing. And then if you have an evaporator coil that runs in a vacuum, that can be confusing too, because you have no leak during cooling, but then you have a leak during defrost. And you're also sucking air into the system, most likely when it's in a vacuum. So with live systems, Jake, that kind of brings me to shaft seals. So what's your experience with shaft seals in the world of open type compressors?
Yeah, so on anything that's open drive where there's a shaft seal, they will leak at a certain point. And some of this equipment actually had an acceptable leak rate, and it was more that the oil was coming out of the seal. So you could monitor that leak rate, and if it got to a point where it exceeded that leak rate, then you would warrant changing that shaft seal out. But if the shaft seals are installed properly and correctly, they shouldn't leak for an extended period of time. But over time, they will wear out because there's usually a carbon seal in there, or some of them have a mechanical seal. It just depends on the type. And at some point, they're going to leak. So that's one of those points that it's just kind of known, right? Shaft seals are going to leak at some point. But if you stay on top of the maintenance, and another thing is when you're working on, let's say, a York chiller, they have oil pump and an oil heater. That's something that you want to keep on even when the chiller is off for the season. Because in Canada, obviously, we run the chillers for comfort cooling in the summer, and most of them are shut off in the winter. So I've seen some facilities where they take the power away from the chiller and their shaft seal leaks. But I recommend to keep the chiller power on, keep the oil pump on, and keep the oil heater on. So it keeps that shaft seal sealed. And they actually have a program in the newer software that every 24 hours it'll run the pump for like 5 minutes to keep that pressure on it. So it reduces the amount of leak rate that could happen on that. So.
Yeah, that's some good experience to hear about specifically, Jake. I know we had this conversation in different aspects before. So in my memory, the one that sticks out is I think there was like a 2-pad rink somewhere in the GTA, and it had 4 recips. And I was doing maintenance there for, I don't know, a handful of days anyways. So the lead machine, and that term means the machine that's going to run primary, so the compressor that's going to run first in the control strategy, is running most of the time. And I'm in there, a few full days on this week, and sometimes there's an ammonia leak, right? And what it was is when that lead compressor turned off, that would run like, I think it's like 15 psig if I'm not making stuff up. I'll look it up while I'm talking. So what are you going to run at a rink? I'm going to use this app again. Sorry if there's background noise. My English Bulldog Lorenzo is snoring pretty loud at this point, but I'll
Shop
check out
dog.
the SST. Shop dog. Okay, so considerably higher than I said. What are you going to be at? 20. It's close. So something like that. Yeah, going to be like something around maybe 30 psig. I'm just guessing here. You're going to run SST below freezing for an ice rink anyways. So that's for ammonia. If you're at that low SST and you're operating at a pressure of like 30 psig and you're running, the shaft seal could be happy with that, right? Like the shaft seal is kind of a weird thing. It's a bit malleable. It's not like a pipe fitting where it's the same all the time. So that shaft seal is going to be good, not leak. And then you turn that system off, and the shaft seal in a Micom reciprocating compressor is located in a suction, and you let that suction pressure come up a bit, whatever it comes up to, that just increase in pressure during the off cycle can cause a shaft seal to leak. So it's just like a funny thing. It's like, oh, the shaft seal's leaking. Turn the compressor back on.
Yeah, for sure. Yeah, pressure, oil pressure, and refrigerant pressure will help seal it. So, another point I was thinking about when you were talking about that evaporator, seeing it in that defrost state where typically it runs at a low pressure, but then if it goes into a defrost state, it's introducing a high pressure, high temperature. So what sparked my brain was heat pumps.
Mhm.
So heat pumps do the same thing, right? They reverse the indoor and outdoor coil now.
Yeah.
So they're going to see pressures in a different state. So you might be running and cooling all year and there's no issue. And then you
Yeah.
go to the heating cycle and it changes the hot gas into the indoor unit and now you got a leak and you don't know about it, right? So this goes back to reading the manual again and finding out what the pressure test is rated for that equipment. I would follow the manufacturer's recommendations because they're going to know the best thing for that system. I've seen some literature where it's 410A and it says 150 psi, which doesn't make any sense to me because the refrigerant operates at a lot higher pressure than that. But when I worked on York VRF equipment, it specifically stated in there that you had to pressure test the whole system at 600 psi for 24 hours and it needed to hold. And I thought that was the best. Like, I know it's a high pressure, but they want to verify that whole system can maintain at 600 psi. It's probably going to run maximum at about 500, maybe up to 550. But they recommended that in the literature. I was like, well, I always follow the manufacturer's literature because they're the ones that put it out. They've tested it and all this stuff. And then if there's an issue, then you can go back to the manufacturer and say, hey, listen, I followed your instructions. What's the next step here? Because it's not doing what I want it to do. So,
Yeah, that's great. And that finally leads us into nitrogen. So you're talking about having to use high pressure nitrogen bottles with an XPR regulator, right, Jake, to get that amount of capacity out? Because
yeah,
with the standard bottle, it's challenging to get more than like 440 or
yeah,
450.
yeah. You'd have to use special equipment to get it up to that high of pressure, right? And you're going to have probably multiple bottles again to allow you to get that pressure up that high. So, because most of the standard regulators, I think they only go to like 400 or 500, I think, on the operating
The
pressure.
outlet pressure, right, Jake?
Yeah, like the tank pressure is going to be a lot higher, like
Yeah.
2000 psi or whatever it is, but the operating pressure. So you'd have to get a special regulator for going up that high, I believe. I can't remember now.
Yeah. No, you're correct. I got an image. I got an image here that I'm looking at.
Oh, perfect. Yeah. Are you able to share it
I
or?
can pull that up. Yeah, there we go. And that leads me into because we got a few minutes left, AJ.
Yeah, a few minutes. Yeah.
So that leads me into what we were going to talk about, anyways. Is this is from an article that I wrote for HVAC Know It All on pressure testing, and we are just going to kind of reference this quickly at the end. So I'm just going to share my screen for everybody who's got eyes on this, and I'll do a verbal on what I'm talking about. Besides that, there we go. It's a nice picture of me and Nicolina, my longtime fiance in Greece. There we go. Good background. Okay, so this image is good because it shows what we were just talking about on the left side, which is called an XPR regulator, and this is a high pressure regulator. And then the one on the right side, not as clean of an image, is a standard nitrogen pressure regulator that everybody's going to be using working on any type of equipment. So we can start with the one on the right. So the pressures that you have on them, you have an inlet pressure from the bottle, and we'll stick with PSI. The sorry, okay. On the right side, you have an inlet pressure from the bottle. So um, nitrogen bottle standard ones like 2500 psi GJ, if fresh bottle.
It's kind of all over the place, anywhere from 2000 to 2500. I think the standard's like 2200, but it's
Yeah.
going to be up around that 2000 psi mark.
So I'll mark this up. You can see that, right? Jake in pink. I got a circle
Yeah,
there. So that's 4000 psi. So a standard nitrogen regulator is well above what you're going to have on a standard bottle. It's very safe. So you can hook it up to 4,000. But the most you're going to get out of a bottle is right where this tick is at 2,500 psi G. That's what you're going to get. So this is the inlet on the right side from the bottle. You can barely see it, but that's the connection that you thread into the bottle. And before I forget, I want to note that is a different connection type than an XPR regulator for safety, so that you don't explode a standard regulator with a high pressure bottle. So that's the bottle side. And then the outlet side, I don't know why I'm having so much trouble with my words. It goes up to 1,000 psi. And I think what is maybe misleading about that is it makes you feel like you can get 1,000 psi out of that regulator. You're like, okay, the regulator says it'll let me put 1,000 psi out. I should be able to pressure test stuff to 1,000 psi. But because of pressure differential and volume of the bottle versus the system you're testing, in practical experience, Jake and I were just agreeing, like, you're not really going to get more than like 440, 450 psig out of a standard bottle with this regulator, right?
Mm-hmm.
All right.
Yeah, the other thing to mention too, when you're working with gauges, the most accurate range is when the needle is vertical. So
Yep.
when you're looking at a gauge, that's kind of the sweet spot that you want to look at, right? So that's kind of the range that it's going to be going to, right? Like
Yes.
if you went all the way over to the 1,000 psi mark there, you're going to be kind of way out of the scale. So on both of these, when they're at, let's say, their maximum capacities, they're going to be mostly in that middle range there. So you can kind of see, why that makes sense, right?
Good. Yeah. So what Jake is saying for everybody that's on the visual, between 0 and 1,000 is going to be 500 psi. So if your needle is here, that's going to be an accurate range to use the regulator within.
Yeah.
And then to finish this, if we move over to the XPR regulator, we got a nice different style handle. You can take this off, so it's easy to store in your drawers. That's great. And then the bottle side is going to allow you to get 6,000 of PSI from the bottle if it goes up that high. So a high pressure bottle is going to be about 4,500 PSIG in a fresh bottle of high pressure nitrogen. So this is going to give you way more capacity to pressure test stuff than a bottle that's at like 2,500. Okay. And the face where you're going to put your pressure out, so that fitting there is going to be your outlet pressure. You have a way bigger range. So this face for the outlet goes up to 4,000 PSIG if you could ever get there. So, the middle range of this is 2,000. And I don't know how high you can get. I haven't worked on CO2 systems, or I haven't followed a manual like Jake has to pressure test to 600, but you're going to be able to get, you know, a lot more pressure out more easily out of a high pressure system.
Yeah, that's great.
All right.
So if you want to just pull up that article and just kind of
Yeah.
show maybe we'll put the link in the description for this year when we get this out there. But yeah, Julian was had the opportunity to publish an article for HVAC Know It All podcast, or HVAC Know It All website, and I think that's great. Any information that gets out there so people can read and understand, and it is great. That's why we're doing this podcast too. We're just trying to share information and help people out understanding concepts. And if you guys are watching this video here, throw some stuff in the comments. We might see some topics, and we can start introducing other things that people are looking for information on. So we got a wealth of knowledge between commercial industrial equipment and even in the residential sector as well. Like I've worked on all different types of equipment. So
Yeah, no, right
I
on,
re-
Jake.
yeah, I recommend checking it out. It's a really good article.
Thanks for that, man. Yeah, we'll link that. So, that's everything that we got for this episode. So thanks everybody for listening. We will see you all next time.
All right, I'm A-Track Jake.
I'm Julian.
We're out.
Bye.